Let us start this lecture with a thought process. One has to pursue question honestly, like a faithful shadow meticulously. One should bear question in mind like a small innocent inquisitive child. It is very important to not only ask the question, but also pursue it vehemently. Unfortunately, with modern education, we are not really asking question and not even pursuing it, even though we are asking sometimes certain question to ourselves. And also this is happening because of very busy lifestyle or a fast lifestyle. So, let us now recall what we learnt in the last lecture. In the last lecture, we basically looked at various methods of measuring the burning velocity, and in all these methods we really looked at the propagating flames and how it is moving and what speed it is moving. From that data, of course, with the help of photographs and also the pressure sensors, we could measure the burning velocity out of it. And three methods we had discussed in the last lecture. One is tube method, other is the combustion bomb method, other is soap bubble method. Each one was having their own advantages and disadvantages. Today, we will be discussing basically about another method of measuring burning velocity, in which the flame will be stabilized, unlike in the previous case in which it was moving or propagating. So, let us look at a Bunsen burner flame. In a Bunsen burner, you might recall that the Bunsen burner was devised by Bunsen in around 1855. It is he who was really discovered the premix flame, and typical flame you can look at in a Bunsen burner, like this is your a tube, and which is having a wall thickness, and in this case fuel and oxidizer are pre-mixed thoroughly, and at certain equivalence ratio. If you look at phi is your equivalence ratio, and then you can ignite and the flame can be stabilized with the rim. See, this is your tube having certain finite thickness. This is your rim of this tube, and which you can call it the rim of the burner, and which helps in stabilizing the flame, because the on the wall of this tube there will be heat losses from the flame in this portion, which will be coming over here, and a flame will be established, a conical flame. This is a photograph of a conical flame. This flame is basically corresponding to the equivalence ratio less than equal to 1. Therefore, you get a very sharp feature and a only one flame, and this is a very curved one, and this portion is curved due to the heat losses to the rim of the tube or the burner, and this portion is curved very much, and the flame is subjected to stretch flame, and this region where it is almost straight. So, it is not subjected to any stretch or the minimum amount of stretch. So, let us now look at that flame in a, another figure which I have shown here, and this is basically being obtained by conducting experiments and measuring the shape of a flame. This is your in a natural gas air flame, and in this case the particles are being introduced at this end, and such that this particle will be moving along these directions. And if you look at, these are basically steady flame, and you can say these lines are the stream lines, and it is diverges in this zone, and this is your inner cone zone. And in some cases, particularly where equivalence ratio will be greater than 1, rather rich flame, there will be some outer diffusion flame will be coming, outer cone diffusion flame will be coming, particularly when equivalence ratio greater than 1, rather rich mixture flame. For mixture, this can come also. And keep in mind that to have this flame, it is very important to have a velocity profile which can give you the conical shape kind of burner, which can be stabilized well. And keep in mind that velocity profile in this tube one can get different depending on the length of the flame. So, if sufficient length of the tube can be provided for the fuel air mixtures to travel, then we can get a fully developed velocity profile, and that will be parabolic in nature, right. If you look at, this is your parabolic in nature, and one has to ensure that this velocity profile or the fully developed velocity profile must be ensured such that you can really get the same boundary condition for different set of readings. So, that is very important what you can have for conducting experiment. So, this is a very important aspect one has to do for conducting experiments, and so that it can be repeated easily, and different equivalence ratio one can maintain so that you can get a various thing. Let us now look at for a one case how this burning velocity, that is S L, is laminar burning velocity. And keep in mind that this, if you look at this axis, if I can say this is your z axis and this axis is your x. So, if I take the velocity, the laminar burning velocity at each location, then I can really find it out what will be the I can plot with respect to x, that is S L versus the x. And keep in mind that in this case the flame will be traveling from this direction towards the incoming fuel air mixtures in such a way that wherever the local velocity, right, will be perpendicular, this is your fluid velocity V and this is your S L at a flame location. When V is the fluid velocity, this is the velocity of fluid, rather I would say is the local fluid velocity, S L is the local burning velocity. The flame will be stabilized as we had seen earlier also, V is equal to S L at any location. So, each place it will be having such that it will be you can have different, and this can be very easily obtained. Earlier days people are using particle tracking method, and nowadays one can have a PIV method. such that what you will do, you will have to find out this velocity v, and then you can say this velocity is same as that. So, locally, and then you will find out v is equal to S L. And when you do that, you will find very interestingly S L is being plotted with respect to x, this is your x direction, right. And you can see that the burning velocity is very higher in this zone. That means, at this zone, right, burning velocity is higher, and in this zone, as I had discussed earlier, the burning velocity is remaining almost constant. After that, of course, it decreases due to the locally heat loss which will be there due to the rim of the tube. So, therefore, this is due to the burning velocity decreases due to heat losses, and this is increase S L due to flame stretch. So, what we will be taking, basically the actual burning velocity is this is the one which we will be taking considering in this burner. So, therefore, it is very important to consider the proper burning velocities, and otherwise it will be wrong. Of course, we will be seeing some other method which is a little crude, but it can give you some average value for the burning velocities. And this whatever I have discussed is basically for the local burning velocity. So, now look at a method which is very simple to do, because just now we have seen that very sophisticated methods is required to measure the local burning velocity on the surface of a flame by using PIV or particle image velocimetry and other very sophisticated instrument. However, in the laboratory we can use a very simple method, and for a stationary Bunsen flame by using one method what we call area method. And what we will do in this case, we will take a tube and then consider basically the velocity profile proper, so that a flame shape will come, and you can take a photograph of this flame and then measure this area of the flame surface, and from that one can calculate the burning velocity or average burning velocity of a flame. And if you look at, like as I told, that a conical flame is to be established at the exit of a tube in which the fully developed flow is being ensured, and proper equivalence ratio fuel and oxidizer has to be maintained, so that a flame can be conical flame can be established. Keep in mind that the local burning velocity must be equal to the local flow velocity, that is very important. For example, if I take here some velocity, let us say this is having, this is your fluid velocity v, right, and then what will happen, I can resolve this velocity into if I take this is your angle alpha into certain angle along with this direction, and then I can resolve this into this direction. So, that this will be v n, this is normal direction, and this is your v t tangential direction along with the flame surface. So, that what will happen, you can the flame can be stabilized only when v n is equal to S L locally in this region. But however, in this case we will be using area average method. So, there might be some velocity profile which will be there here in this case, this is. But however, in this calculation what we will be doing, we will be taking the average velocity of this profile. This may be like this average velocity which will be remaining, this is hypothetical. This is your V average that we are considering as some hypothetical velocities. As I told, the flame shape will be influenced by the exit velocity profile and heat losses to the tube. Length of the tube must be ensured such that fully developed flow should be there at the exit of this tube. And for stationary flame, we can have a mass balance, that means whatever the flow is passing through here in this flame surface, which will be taking. So, if you look at this mass balance, we can say this is basically unburnt fuel air mixture, and which we assume that in this surface also that this will be unburnt. So, we can say that this mixture, this is the average velocity of fuel and oxidizer mixture. So, if I take that out, what I will get? I will get this rho u V average, that is the mass flow rate which is passing through the tube, into A T. A T is the area of, A T is basically area of tube. This is that direction, this is your basically cross section of A T, is equal to rho u, because this is the cold side and this is the hot side, this is your hot side and this is your cold side, this is your cold mixtures, right. Then that will be unburnt temperature, density of the unburnt mixtures, into S L. S L is the average burning velocity of this flame and is equal to into the A F. A F is basically the flame surface area. So, this will cancel it out. So, you will get basically S L is equal to V T A T by A F. So, as I told that this is basically A F is the conical surface area of the flame, which can be obtained by the photographs. Of course, nowadays people are using image processing to find out this conical surface area of flame. Earlier days people were measuring by taking a still photograph, and this is one of the method which will be very crude one, but it will give you some values such that it can be utilized. Unlike the previous method, this is relatively crude one. As I told earlier that this method is known as the area method. There is another method which is known as the nozzle method. Generally, the nozzle will be designed in such that there is a increase in velocity, and the velocity profile at the exit of this nozzle will be almost like a flat velocity profile or one dimensional velocity profile, except in this region there might be little bit change because of development of boundary layer. Keep in mind, for nozzle design one has to have a decrease of area, the area ratio must be greater than the 4, is a thumb rule which is being used for designing a nozzle to have a velocity one dimensional velocity profile. And keep in mind that in this case the velocity V u is same everywhere. So, that if you can look at, this is basically your V u, and then from this photograph what you can do, basically you can measure this angle alpha. If I know this angle alpha, it is very easy to find out S L, and if I resolve this V u into two component, one is along the flame surface V u t, that means the unburnt velocity, tangential velocity or tangential unburnt velocity, on the perpendicular to this flame surface, that is normal component of unburnt velocity. And keep in mind that flame is traveling in this direction with S L. So, therefore, S L is equal to V u n, and what is that V u n? V u n is nothing but your V u sin alpha, because this is your angle, alpha is the angle of flame cone, this basically half angle. So, then I can get directly the burning velocity by measuring the angle of the flame cone. And of course, the V u is already you know, because you know the mass flow rate, and you can get very easily by knowing the density and also the cross sectional area of the nozzle. So, this method is basically known as nozzle method, which is superior as compared to area method, but problem with this method is that it can be used for a very limited range of the fuel air mixtures, because it is difficult to stabilize the flame in this nozzle as compared to the Bunsen burner, in which generally the area method is being used in the laboratory, unless you are having a very sophisticated instrument to use like PIV and also particle image velocimeter, where you can measure the local velocity, not the average velocity. So, the also there it is very important to be careful, otherwise you will be land in getting some number which is not really congruent with the reported measurements of the burning velocity for particular fuel and air. So, disadvantages of this method that heat loss to the wall cannot be avoided completely, therefore, there might be small error in that, and other is the burning velocity does not remain constant along its surface, and the flame stabilization for large diameter is difficult due to the flash back, because it will be flame will be entering into the burner, particularly when the fuel air mixtures is either the lean or maybe toward the when fuel air mixture is basically lean, the flame will be trying to flash back due to the low burning velocity. And let us look at example like where we can calculate the burning velocities. The example is very simple one, that is in a Bunsen burner of 10 mm diameter, a conical laminar flame with a flame height of 5.1 centimeter is established consuming 19 LPM of methane air mixture, and determine the laminar burning will SL and also average velocity of methane air mixtures. So, it is already given that is a conical flame here. So, and the height of the flame is given, and it is having the mass flow rate or the volumetric flow rate is given for the methane air mixtures. It is given HF, the flame height is 5.1 centimeter and diameter of the tube is 10 mm, and the mixture is something 19 LPM. LPM means liter per minute, and we will have to find out Vm, the velocity of the methane air mixture, average velocity of methane mixture, and SL, burning velocity. So, if you look at what is given is a conical flame. So, it is HF is given, and this radius or the diameter is given, this is 10 mm. So, we can find out very easily, that is SL is equal to Qm by AF, and we can also find out Vm is equal to Qm divided by AT. So, if you look at AT, AT is very easy, that is pi by 4 d square. If you do that, multiply it by that into 1, because 10 mm I can say this is basically 1 centimeter, then it is nothing but your 0.784 centimeter, and AF I can take it as a right angle cone, and then I can find out that AF will be pi r, r is basically d by 2 root over r square plus h f square, and this is nothing but your r. So, if you do that, you will get pi into 0.05, 0.05 plus 5.1 square. So, you will get 8.02 centimeter square. So, similarly, we will get basically V m is nothing but your 19 LPM divided by 60 into the area is 0.784 into 1000 is will be 403.91 centimeter per second, and SL is similarly 19 into 1000 divided by 60 into 8.02, you will get 39.48 centimeter per second. So, this is a method by which you can really calculate the burning velocity. Okay, thank you very much. We will stop over here, and in the next lecture we will be discussing about few more method how to measure the burning velocity.